Drop a pencil into a glass of water, and right at the surface, the solid wood appears to snap in two. Usually, we expect light to move in a perfectly straight line, and in the vacuum of empty space, it does, traveling at a constant 300,000 kilometers per second. But those rules shift the moment light enters a transparent medium, like water, glass, or a diamond. As the rays pass from the air into these denser materials, their direction changes. They bend. This is the phenomenon of refraction. Moving beyond the visual trick means finding the specific rules that determine how light behaves when it hits a new surface. We can isolate this in a lab. By firing a single laser beam into a water tank, we can observe the exact angle of that bend. This happens because of optical density. Imagine a car speeding down a paved highway. If it veers slightly off the road so the right tires hit the muddy shoulder, the mud drags on those wheels, slowing them down. Because the left wheels are still moving fast on the pavement, the entire vehicle pivots. Light experiences a similar pivot. When it moves from the air into denser water, the medium drags its speed down, forcing the beam to change direction. It's a common misconception that this slowdown happens because light particles are physically bumping into water atoms, like a person struggling to move through a crowded room. The cause is actually quantum mechanical. Incoming light waves excite the atoms in the medium, which then produce their own electromagnetic waves. These waves interact, creating an interference pattern that reduces the apparent speed of the light. This subatomic interference is the physical reason that every refracted beam of light bends the way it does. If we focus on the exact point where that laser hits the water, we can map the geometry of the bend. This diagram shows the relationship between the light and the normal line, the vertical boundary perpendicular to the surface. In the top half, we see the angle of incidence, or alpha 1, which is where light approaches from the air. In the bottom half, we see the angle of refraction, or alpha 2. Because water is denser than air, the light path is pulled toward the normal line, creating a narrower angle. By labeling the different media as N1 and N2, we can use Snell's law to calculate the bend. Knowing the density of the material and the incoming angle, we predict the light's path before it even hits the surface. Framing this bend as a geometric equation allows us to calculate the path light will take through almost any medium. If we intentionally curve the surface of a glass medium, we can force multiple light rays to bend and converge at a single focal point. This controlled convergence can correct for biological flaws in the human eye. By placing a specific curve in front of a blurry eye, we can ensure light lands exactly on the retina. This kit contains dozens of test lenses used to find the specific curvature needed to compensate for a patient's vision. Scaling up this curvature allows us to capture incredibly faint light from the cosmos. This massive refracting telescope uses lenses to focus distant starlight. By controlling these curves, we've extended our sight from the level of the cell to the edge of the galaxy. Refraction has a limit. When a light ray approaches a boundary at an extremely shallow angle, it reaches what we call the critical angle. At this point, the light can no longer escape into the second medium. Instead, it undergoes total internal reflection, bouncing perfectly back inside the first material. We use this to trap light inside thin strands of glass called fiber optic cables. By bouncing encoded light pulses off these internal boundaries, we can guide data across entire ocean floors at the speed of light. This modern infrastructure relies on the same physics seen in a simple glass of water. The same shift in speed that breaks a pencil is what carries the pulses of light that connect the modern world.